Most people think polynomials are just simply a list of complicated terms. However, that is a wrong belief. In fact, polynomials can be easily summarized by one single word, starting with R. Today, we will be exploring that. And alongside it, we will be starting 2 lectures based on functions. Before we dive into today's lecture, let me show you the unit overview of AMC12 algebra. As you most likely will recall, we have first covered equations and inequalities. This is the foundational stuff of algebra, so it makes sense to talk about it first. Next, we talk about sequences and series, and that reason might seem a bit abstract to you. However, we'll reveal that today. And starting from today, we'll be talking about functions, and the first of which is graphing, because graphing functions is important, then polynomials, then trig functions. We'll dive into what exactly these are in a moment, and then after that, exponential arithmetic functions. Then after that, we'll expand on both equations and inequalities. For inequalities, we'll explore advanced inequalities. For equations, we'll explore what lies beyond those solutions that we deem unsolvable. For instance, x squared minus 2x plus 2 equals 0. Now, back to this part, and let's seek some logic here. In fact, all we're talking about down here are functions. However, they are continuous functions. That means if 2 points are defined, then the bits inside them, between them, are also defined. However, for this, sequences and series, I treat these as functions as well. However, they are discrete functions. For instance, a sequence can be denoted as a of x, where this simply refers to the x term. Similarly, a series can be s of x. So that is the logic behind this unit. And currently, we will be visiting these 3 areas. These 3 areas aren't too hard, and they're already what you know. So we'll be building on top of the middle school knowledge, and it won't take too much time. So we'll combine these 3 topics into one video. Before we dive into the main course of this video, which is polynomials, let's first talk about functions, what functions are. Essentially, you can treat functions as a mysterious box. It only has one slit through it, and there is a screen displaying something. You can pop a number in through the slit. Then after that, something shows on the screen. However, the nice thing about functions is that it is deterministic. That means, suppose I throw in one number a, and this number a is a constant number, it doesn't change, then the value that is going to be displayed here, f of a, doesn't change as well. However, sometimes some bad values might be thrown in and the box explodes. For instance, suppose the function f of x is equal to 1 over x. If you try to plug in x equals 0, the box explodes. So when we're talking about functions, we need to be careful of when the functions are defined as well. That's a quick overview of what functions is, and now let's dive into the good part about graphing functions. So in the second video, I promised you that we're going to justify that plugging in special values here for this inequality works, and we're going to prove that today. So essentially we have this equation, and then it's supposed to be less than 3. Then what we can do is actually graph it. And here's the graph. The green line here is y equals 3. And the red lines represent x plus t over x minus t, while t can be changed. So since t ranges from -1 to 1, let's see what happens when we pull it from -1 to 1. It first closes in, then at some point it pops, which is t equals 0. Because it is quite easy to understand when t equals 0, the original equation equals x over x, which is simply 1. And then when we keep on moving, the same pattern appears again, and then it slowly moves towards the other sides. Now, since we're asking for which x, y is always less than 3. If we focus on the intersection points, for instance, this one, then when we move t, you notice that intersection point is moving in all the way until we reach t equals 0. So what this means is the point x equals 2 always lies below or on the line y equals 3. And of course, the points between 0 and 2 also follows this pattern. And when we move across t equals 0, of course, points on the right side of the y-axis always lies below y equals 3. So we have successfully solved that the interval 0 to 2 is the solution. And similarly on the left side, negative 2 to 0 is also the solution. So the answer to the entire inequality would simply be -2 to 2. And we're done. So basically what we did here is that we treated the left side as a function. F of x is equal to x plus t over x minus t, while t is a parameter. And then we treated this 3 as a constant line. And it just naturally makes sense because you're essentially trying to find the region that is below that constant line. Let's demonstrate another example, and this time we will graph this problem by hand. The problem essentially asks tangent 2x is equal to cosine x over 2. How many solutions are there on the interval 0 to 2 pi? So in case you're not really sure what this is, let's first do a review, which is basic functions, or also called elementary functions. These functions include a lot. So here on the left side of the screen, I have a list of all the elementary functions, and we're going to take a look at them one by one. So here, this is y equals x squared, y equals x cubed. And similarly, these are just negative powers, and these are half powers. And this thing looks like very much a crazy graph. However, what I'm trying to show you is that all of these can actually be called one single thing, which is the power function, x to the nth power. And here x is the variable. So as you can see, as long as n is greater or equal to 1 and n is an integer, when we add up power functions, we gain polynomials, which is the main course of this video. Next up, we also have trigonometric functions, which are these. So as you can see, the trigonometric functions, they look very quirky because for sine of x and cosine of x, this is just a cycle. For tangent of x, it is blowing up a lot. At the end of this lesson, we will go into a deeper dive of the trigonometric functions, but we'll leave it here for the moment. And the final two functions are the exponential function and the logarithm function. We won't go too deep into that, but these are also basic elementary functions. So just take a look, and we'll introduce that in the next lesson. These are the basic functions. So now let's go back to the problem. This problem is actually an AMC12 problem, and I give it a difficulty of 2. So let's try and solve this. For this problem, I am not emphasizing the trig functions, so I'm just going to show you what the functions look like. So for tangent of 2x, let's graph this thing by hand. And since we're focusing on the interval 0 to 2 pi, we'll put it here first. And then let's just first plug in some special values, okay? So tangent of 2x, when x is equal to 0, recall that sine of x at that point is also equal to 0. So tangent of 2x, where x is equal to 0, is 0. Now, for tangent of 2x when x is equal to 2 pi, that is essentially tangent 4 pi. Tangent 4 pi is again 0. What happens in the middle? When we put pi here, tangent of 2 pi is again, unfortunately, 0. And if we close in a bit further, pi over 2, we're in luck, because tangent of pi is again 0. So we're really graphing a lot of zeros at the moment. So similarly, 3 pi over 2 is also 0. But now, finally, we have something interesting when x equals pi over 4. Tangent pi over 2 is positive infinity. And then, similarly, this point, which is 3 pi over 4, this point is negative infinity. Correct something right now because I realized I made a mistake when explaining. Actually, since tangent of x is equal to sine of x over cosine of x, when cosine of x is equal to 0, you can treat it essentially undefined. However, for instance, we know tangent pi over 2 is equal to an undefined value because cosine of pi over 2 is 0. But if you just twist this value over here by a very small value, epsilon, where epsilon is greater than 0, then this term is essentially somewhat close to positive infinity. And if you add it by a small value, then this thing is negative infinity. So essentially when graphing, we need to graph both points. So we can treat pi over 4, even though it is not defined, we can treat it as simultaneously appearing at positive infinity and negative infinity. So we obtain this graph. Now let's focus on cosine of x over 2, and we'll do something similar with that. To save time, let me just show you what the ultimate result is. And here we go. This is the graph we're looking for. Well, so essentially somewhere over here, this point, this is 2 pi. This is the right side of the interval we're focusing on. And if we move all the way over, this is the left side, which is 0 and 1. So as you can see, in between these 2 points, there are 1, 2, 3, 4, 5 solutions. So the answer to this problem is simply 5, and we're done. So as you can see, even though directly calculating this thing might be hard, but graphing is a great way. Graphing gives you a clear understanding of what is going on, and sometimes it can visualize solutions. Because even if you don't have such an accurate graph, for instance, mine is not very accurate, But you can see if we just graph it like this, it's very clear that there is 5 solutions. That is the power of graphing. So here are some tips for graphing a good graph. First of all, I would recommend you find some set points or constant points. For instance, in this case, we first analyzed multiples of pi because they're special. Then you can find the monotonous intervals. Because when graphing, we generally doesn't really need the accurate information, but we need to understand how the function is going around. So whenever you obtain 2 points and you know in between them it is monotonous, then you can just forget about that interval and just draw a line between them, and it is already good enough. So combining these 2 techniques, you can probably draw a decently good graph, and that is exactly what we did over here. Next, let's look at something not very function related, but also related with graphs. So essentially, the problem is asking, we have information like this. We're supposed to find the maximum value and minimum value of C. Let's do some manipulation here first. So we know C is equal to 2 minus A plus B, and meantime we also know C squared is equal to 12 minus A squared plus B squared, right? And now what we do is that we treat C as a constant, treat A as the variable x, and B as the output of the function f of x, or y, in case you're plotting it in the coordinate plane. Similarly for this as well, so we can draw this out, which looks like this. Here again, C is a slider because it can be changed. Essentially, we're asking, what is the minimum value of C such that there is still a solution to the equations above? For a solution to exist, we need a point both on the circle and on the line. In this case, this satisfies the constraint. Let's see what happens when we make C even smaller. There are no more solutions because there is no intersection. So C, in this case, must lie above -2, and when we move upwards, we reach the maximum, again, somewhere between these points. So again, this is a point where the line is tangent to the circle, which appears when C is equal to 10/3, and it can be solved. Essentially, the way to solve it is just to make sure both equations works simultaneously and then try to calculate the determinant. So in this case, the biggest value for C is 10/3. That means the answer to this problem is simply 10/3 minus the minimum, which is -2, and we are done. So again, you can see the power of graphing. It can be exceptionally good at giving you hits. For instance, in this case, it hinted you that when the maximum or minimum value occurs, x is equal to y. Finally, let me show you yet another example of a great graphing problem. Let this function be the floor of x, or the greatest integer less than or equal to x. How many real numbers x satisfies this equation? This thing really resembles the problem we solved in the second video related to integer parts. And again, this problem is not an easy problem. It is the 24th problem of a test. However, in my opinion, this problem only has difficulty 3 because we can graph it. First, let's study the equation. Define this as x minus floor of x. Then x squared is simply 10,000 times this new symbol here. This is a clean way to shorten the formula. And now here, it's really difficult to graph this thing. Then let's graph a smaller example. Let this value be 16 for now. We're trying to study x squared is equal to 16 times the decimal part of x. What will happen here? First, we graph x squared. It more or less looks like this. It's really difficult to draw on the iPad, but just make do. And then now let's graph this. So since this value ranges between 0 and 1, non-inclusive for 1, and that means 16 times that has a maximum value of 16. So on each interval, there is a monotonous region, which essentially looks more or less like this. We're using this to represent non-inclusive, and this to represent inclusive. So this is repeated over and over again. We want to know how many real numbers x satisfies this equation. Well, essentially, it's just asking, what is the greatest number x such that x squared is still lesser or equal to 16? Or in the original problem, is what is the greatest number x such that x squared is less than or equal to 10,000? We obtain the new inequality, -4, +4, and in this case, -100 to +100. So is the answer 201? No, let's check, for instance, x equals 100. When x is equal to 100, x squared is equal to 10,000, and the decimal part of x, however, is equal to 0. Because recall that this thing is non-inclusive. So in fact, we have to roll out x equals 100 and negative 100. Both are incorrect. So the true answer here should be 199, and we are done. So again, this is the power of graphing, and sometimes reducing the problem actually works as well. You can first solve an analogous problem, and then after that, expand the scale of the problem so that you can solve it easily yourself. This is the first part of today's lecture. It's all about graphing. Now, into the main course, polynomials. If I ask you to write a polynomial p of x, which is essentially a function in itself, how many ways can you think of writing it? The most obvious two are sum form and product form. Sum form I will denote as this, right? Or if we expand it, it looks more or less like c0 times x to the 0th degree plus c1 times x to the 1st degree, then to the 2nd degree, etc., all the way up to the nth degree. There is also a second form, which is the product form. This symbol means the product of, similar to the summation sign. And then in this case, it can be written as something like this. So essentially, this is the factorized version of p of x. Or in an easier way to understand that, it's just p1x minus q1 times p2x minus q2, etc., all the way up to pnx minus qn. This can provide you information on this factorization, thus also the information on the roots. This one, however, can provide you information on the coefficients, and this one is much more commonly seen compared to the factorized version. Here, I plan to introduce something called the basic version of a polynomial. In this case, the basic version is essentially defined, for instance, qx, then the term with the highest degree must have coefficient 1. Or every single factorization must be in the form x minus ri. Any polynomial can be scaled from a basic polynomial, so you can study basic polynomials when you only care about the roots, because the roots won't be scaled. For instance, we currently have a polynomial. It looks more or less like this. And essentially the reason I'm putting these terms here is I'm trying to show to you that polynomials are actually just sums of power functions. And then when you pull a around, you can obtain a lot of functions. It is just going to get stretched. However, notice the roots never change. No matter which direction you go, the roots never change. But you're going to obtain a lot of functions. So the basic version, it's more simple compared to the general version, because the highest degree is 1, so the roots can be written cleanly with one single number. Now, I would like to study the conversion between the sum form and the product form. For simplicity, we will be studying the basic polynomial. So for a basic polynomial p of x, it can be factorized as something like this, where z1, z2, all the way up to zn are all roots. Now, when we expand this stuff, what happens? You can visualize this in a nice way. Think of every single product as a row. So to obtain the term x to the nth power, there is only one single way, which is selecting x from every single row. So the expanded version is simply x of n. And then next, when we focus on x of n minus 1, things get a little more interesting. Because essentially what that means is we will select all the x except 1. Then in this case, if we don't select x, we have to select this. So there are n ways in total to do this. That means the coefficient is actually negative z1 plus z2, etc., all the way up to zn. Similarly, you repeat the same process for x to the n minus 2 degree. In this case, the result is z1 times z2 plus z1 times z3, essentially every single possible combination of two roots. And then we can repeat this for essentially any term, and ultimately in the end, we also get the product of all the roots. And this negative sign comes from the fact that there is always a negative sign in front of the roots. So for instance, if there are 5 terms in the end, then multiplying negative z1, negative z2, etc. to negative z5, that is negative. But if there are only 4 terms, then it is positive. So we have to apply a negative 1 to the nth degree here. So therefore, the coefficients in the sum form can provide information about the roots in the product form. And generally what is most useful are these: sum of roots and product of roots. But of course, sometimes we might also need other things as well. For instance, in this case, the sample problem I have here asks for an expression related with roots. And this really hints that we should use what we just discovered. That means we can first list out p plus q plus r is equal to -2, pq plus pr plus qr is equal to -1, and then pqr is equal to -3. This expression here can be expanded. It is essentially equal to pqr squared plus 4 times pq squared plus pr squared plus qr squared plus 16 times p squared plus q squared plus r squared, and ultimately plus 64. Don't forget the constant term. And then next, we already know this, so we have to find a way to represent p squared, q squared. We have to find a way to represent this messy term. The way to go here is actually this thing is pq plus pr plus qr squared minus 2pqr times p plus q plus r. You can verify this yourself. And then for this thing down here, this is p plus q plus r squared minus 2 times pq plus qr plus pr. And since we know all of these, we can plug them all in and calculate. We discover the answer in the end. I won't calculate the detail. Now, this original problem is from AMC12 2020 4A problem 15, which I give a difficulty of 3. However, let's change this problem slightly and see if we can discover a new way to solve it, which involves changing this equation. Now, your instinct here might be to factorize it. Exactly, that is the way to go. Then, you might notice that since the above expression here is equal to x minus p times x minus q times x minus r, because this is already a basic polynomial, then you can do something, this is f of x, to this. See if you can discover it yourself. In fact, what is going on here is essentially this is f of 2 times f of -2. And we simply have to plug 2 and -2 into this expression, and the solution is reached. So for the original number, this can also be solved with this technique, but it proves to be a little more difficult to factorize this, so we won't talk about it now. If you know the answer, you can tell me in the comment section below. That concludes our talk about the famous Vieta's formula. This is essentially what we discovered, the sum product form relationship with coefficients and roots. Now, let us review this page. Did you discover something interesting here? We mentioned there is this keyword starting with r. Well, it is not roots. Then what is it? In fact, since we have written the polynomial in this product form, is it possible for a polynomial to be written in product form and sum form? Like something that perhaps looks like this. As a demonstration, I'm going to use a quadratic polynomial. For instance, f squared plus 2x minus 4. We can write this as x squared plus 2x minus 3 minus 1, which is x minus 3 times x plus 1 minus 1. This is a product form with a little bit of a sum at the end. So this is what I'm referring to as the product sum form. In fact, the standard way to represent it here is f of x is equal to p of x times q of x plus r of x. Again, r is appearing again. So everything here are polynomials or constant values, and the requirement here is simply the degree of r must be less than the degree of q. Such a form is obtained by dividing f of x with q of x. That thing has a quotient of p of x and a remainder of r of x. This is the true important thing that I'm talking about. So the fill-in for our keyword is remainder. Suppose r of x is equal to 0, then that means q of x divides f of x. However, sometimes this is not true, so we might aim to find the remainder of f of x divided by q of x. And you might be wondering, why is this significant? Just think about plugging a value into f of x. What is happening there? What might appears to be true, for instance, when you're plugging in the value a, what appears to be happening is that you are plugging a into every term of the sum form and then adding everything up, so you ultimately have the result. However, a better way to understand this is that, in fact, you are dividing f of x by x minus a. And then you are trying to find the remainder r of x, and then plug a into r of x again. Or in a simpler way, f of x can be written as x minus a times p of x plus r of x. Since you're plugging in a, then this term is 0, so you're left with the remainder. So this is the true functioning thing behind polynomials. And I bet you probably haven't heard this before, but I think personally, I think this is the true logic running polynomials at this stage of studying math. In the future, of course, polynomials is a really menacing topic, but at this stage, this is the simple way to understand it, and this is the most logical way to think about polynomials. So that means it is high time we try to discover how to find the remainder of a polynomial divided by another polynomial. Let's start with this example. We're supposed to find x to the 4th degree mod x minus 1 and x minus 2. Remember, r of x, the degree of r of x is always less than the degree of q of x. And in this case, q of x is equal to x squared minus 3x plus 2. So r of x can only be ax plus b. This gives us the first way, which is essentially just value plugging, because we can represent it as the remainder form, right? We mentioned about this. We're dividing by q of x. Just treat this as q of x and this as f of x. This is very familiar. Then what we can do here is we just plug in x equals 1. For x equals 1, x to the 4th degree is 1. This part is 0, so r of 1 is 1. When we plug in x equals 2, x to the 4th degree is 2 to the 4th degree, so it is 16. So r of 2 is 16. Now we also know r of x is equal to ax plus b, so a plus b is equal to 1, and then 2a plus b is equal to 16. Now you can solve a equals 15 and b equals negative 14, so r of x is actually 15x minus 14, and we're done. We have successfully found the remainder polynomial. Next, let's tackle another example. This time you aren't given the factorized form, so you don't know the roots. Assume you don't know the roots at least, because I could have given you an example like x squared minus x plus 2, and this thing doesn't have real roots. What then are you to do? This time, let's set up a modular equation. What does that mean? Imagine this function. This function divided by x squared minus x minus 1 is evidently 0. So let's write it like this. What this means is the function over here divided by the function in the parentheses gives a remainder of 0. Then we can move it to this side so that x squared gives a remainder of x plus 1. Still mod that same old function. This means x to the cube is equivalent to x times x squared, which is equivalent to x times x plus 1, which is equivalent to x squared plus x, which is equivalent to 2x plus 1. All under mod x squared minus x minus 1. Why these arithmetic rules can apply here, you can try to derive yourself, or I'll explain this in the number theory section. But at the moment, this is just a part of polynomial math that is related to remainders. So you just have to accept it and listen to it right now because it's part of algebra. Just assume it is true, then we'll prove this in the future. Similarly, x to the 4th degree is x times 2x plus 1, which is 2x squared plus x, which is 3x plus 1. So x to the 4th degree divided by x squared minus x minus 1 gives a remainder of 3x plus 1, and we are done. Oh, actually 3x plus 2 here, not 1. So this introduces two methods of finding the remainder. One, plugging in special values, using the fact that plugging in values to a function is essentially finding a remainder. Or the second method, using modular arithmetic and just deriving it step by step. For example, we have 2022b, problem 20 from AMC12 with a difficulty of 4. Essentially, we can set up equations of these. We are to find the polynomial x with the least degree of these two properties. What is the sum of the squares of the coefficients of that polynomial? Of course, this polynomial has to be to the 3rd degree to be properly divisible. So we can set it as ax squared, ax cubed plus bx squared plus cx plus d. And then from the first, and then now we can analyze this polynomial under the constraints. For the first constraint, we know x squared is equivalent to negative x minus 1. And similarly, x squared, x cubed is equivalent to x times negative x plus 1, which is negative x squared. minus x, which is x plus 1, minus x, which is in fact 1. So px under the modulus x squared plus x plus 1 can be written as a plus b times negative x minus 1 plus cx plus d, which can be rewritten to negative b plus cx plus a minus b plus d. We can go by the same path of analysis to obtain p of x under modulus x squared plus 1 is equivalent to, we can't say equal, this. And again, we reduced the degree of p of x. So equating the coefficients, because we know that negative b plus c is equal to 1 because here it is 1, here it is 2 because there it is 2, here it is 2 because there it is 2, and this is 1 because this is 1. You solve the system of equations, and solving this gives, how to solve yourself, x cubed plus 2x squared plus 3x plus 3. And we're done. We can just add up the squares of the coefficients, and the answer is 23. Hooray! That is not an easy problem, but we solved it smoothly. So for the final bit of the session, I just want to talk a little bit about trigonometric functions. These are just for your better understanding of lessons in the future. So we'll just have a lightweight overview of trig. Essentially, in high school math, we treat trigonometric functions as a function, rather than what we did in middle school, which is we treated it as a component in geometry. In algebra, we essentially have a circle. The circle is horribly drawn. Let's try again. It's much better. Whenever we select a point on this circle, for instance down here, this point has a degree of theta, or you can also go this way. When you're going counterclockwise, theta is growing positively. However, if you're going clockwise, theta is growing negatively. And whenever this occurs, this point is simply cosine of theta and sine of theta, because the radius of this circle is 1. This is what we call the unit circle. It is really easy to understand. Take a perpendicular line here. Since this is 1, then this is cosine of theta, and this is sine of theta. So this is a way to extend the definition of trig functions beyond the 90 degree. And of course, here we are also treating it as 90 degree as pi over 2, rather than the 90 degrees, because this is essentially referring to the length of the radian. This is pi over 2, the arc, the length of the arc. So this expression is essentially referring to the length of the arc. With these basic knowledge, we can take a look at two beautiful graphs related with trigonometric functions. First up, we have the definition of the function. So in this case, currently we have a slider from negative 2 pi to pi. And up here, we have a circle. This is the demonstration of the unit circle. Focus on what is occurring when I move k. You see, the dot is moving around the circle, while the functions cosine of x, sine of x, and tangent of x is moving around as well. And you can see them climbing the function around and around. And I'll put this in the description in the materials again, as always, so you can play around with this thing yourself. It is really fun just to look at how the dots are moving and how sometimes the tangent function just shoots off and appears back down. The next visualization is related to how sometimes trig functions, they can be manipulated so that they don't look like what they appear to look like originally. So a standard sine function would have looked like this. And you can use these sliders to change the sine function. Because when you change k, it is going to be scaled on the y-axis. The y values are going to change alongside k. Now, for the a value, we are essentially manipulating the length of the waves. So when we move a around, you see the length of the waves change. It can become closer, or it can separate out, become closer, separate out. And then for t, it is essentially an offset. So when you move t, the entire wave is just going to move on the plane. And then lastly, this thing is an offset on the y-axis. The y value is going to change when you move this. So this is a nice visualization of how you can change a trig function. Be sure to check this out in the materials down below. You can play around with it and have some fun. I think the functions are really interesting, especially when you put them onto Desmos or another graphing calculator. And that essentially concludes today's lesson. And let's take a look at homework. Do some algebraic manipulation, then try to graph it in the coordinate plane. See if you can do it properly. Problem 11 requires the Vieta formula, and this can help you train your experience with this very famous theorem. Problem 12 is also quite a cool problem from AMC12. I would say the difficulty is around 3. Last one might be 2.5, again a tricky problem. This one has difficulty 3. So you can try to solve it yourself. Try to find the remainder. And I think just using the techniques you learned and some implementation of the problem solver's toolkit, it won't be hard. And that's all 3 of today's homework problems. So I hope you enjoyed today's lesson. It has been a long one. We have covered the majority of functions, and I will see you 2 days later, and we'll talk about the last 2 functions, which in my opinion is the most interesting functions. We'll save the better for last, and see you next time. Peace until then. Bye.